Welcome to the Deep Dive. We're here to extract the most vital, battle-tested knowledge in tech and, well, deliver it straight to you, making you instantly well-informed. Today, we're embarking on a really intensive exploration of system design. It's a skill that truly separates those who just use technology from those who actually build it at immense scale. And this isn't just theory. We're talking practical, hands-on approaches for building robust, scalable systems. You know, the kind that solve real-world problems, the kind you'd find running in production at top tech companies. Our mission for this deep dive is, frankly, ambitious but clear. We are going to meticulously unearth every crucial concept, every single powerful pattern, every fundamental technology from our curated sources. The goal, to equip you with a crystal clear, truly in-depth understanding of system design. Accurate, really, to what you'd actually encounter in production setups at places like FA. No detail overlooked. Every nugget of knowledge extracted and presented, all designed to help transform you into an even more formidable system design practitioner. Think of this as contributing to your own personal magnum opuses on the subject.
And that really hits a nail on the head. System design is fundamentally about making informed architectural decisions. It's not just knowing what solutions exist, but deeply understanding why a particular solution is the right choice for a specific problem. And, crucially, how to expertly balance those inevitable trade-offs. You always have trade-offs, so this deep dive offers a systematic way to navigate common challenges, things like handling massive continuous streams of data or ensuring rock-solid consistency across, countless distributed components. We're aiming to move you beyond just recognizing the terms to, well, truly mastering the domain.
Okay, let's dive right in then. We're kicking things off with a deep exploration into stream processing. This is a challenge that comes up, constantly in system design discussions, right? And we'll be focusing on Apache Flink, which is a particularly powerful tool for this job. You'll not only get how Flink is used, but maybe more importantly, gain a real conceptual understanding of how it operates under the hood. Because that deeper insight, that's crucial for confidently answering those follow-up questions in an interview and for logically defending your architectural choices.
Yeah, that's a great point. And it's important to clarify up front, while Flink can do batch processing, its real strength, especially in the context we're discussing, distributed systems, interviews that strength lies firmly in stream processing. So for our deep dive today, we'll really concentrate on Flink as a stream-oriented solution.
Perfect. So let's begin with the absolute foundation, streams themselves. What exactly is a stream here? Think of it as an unbounded, continuous sequence of data elements flowing through your system, like an endless river of events constantly being generated. So, for example, a single event, maybe a click, might look something like this. Jasana, use Agrid. 123, action, click, timestamp. 2024 0101 T 00000.000000000. And that's just one tiny drop in this, ever-flowing stream.
Exactly. And Flink gives you this comprehensive toolkit to manipulate these streams. You can slice the data, transform it, aggregate values over time, recombine different streams. Lots of possibilities. A really key distinction, maybe from something like Kafka's append-only logs, is that Flink streams don't inherently require, say, offsets or persistence within their definition. Instead, Flink manages durability and fault tolerance through its powerful checkpointing mechanism. Think of a checkpoint as a system-wide snapshot of the application state. It's taken periodically to make sure data is safe. We'll definitely dig into checkpoints more later.
Okay, checkpoints for durability. Got it. Next up are operators. These are like the building blocks for transforming data within Flink.
You can think of an operator as a component, right? Takes one or more input streams, does some computation or transformation, and then produces one or more output streams. And what's really powerful, you mentioned, is that these operators can be stateful.
Oh, absolutely. That statefulness is a cornerstone of Flink's capabilities. It lets you process complex business logic reliably over time, but for Flink to give you those scaling and fault tolerance guarantees, it must manage that operator state internally. That's non-negotiable. So what that means is if a processing node crashes, Flink can just seamlessly restore the state from a previous checkpoint and resume processing exactly where it left off, no data loss. And Flink offers several types of state for different needs, but the most common ones you likely run into are value state, just a single value per key, and maybe list state or map state if you need to store collections associated with a key. Okay, let's make that more concrete. Say we want to build a simple click counter in Flink. We need to track clicks per user. Flink lets us define essentially a state variable for each user's count. So when a click event for user 123 comes in, Flink grabs their current count from their state variable, dot increments it by 1, and then updates that state variable with the new total. And Flink handles all the messy stuff behind the scenes, right? Making sure that counter is durable, consistent, restored after failures.
Precisely. It lets you build sophisticated long-running analytics right inside your stream processing job. And the absolute crucial concept, the thing you have to remember, is that Flink must know about your state explicitly for it to be checkpointed and restored. When you use Flink's mechanisms to declare and manage state, you're telling the framework, hey, this state matters. Keep it safe and consistent for me. That's what enables those exactly once processing guarantees for stateful operations. It's not magic, it's designed in.
Okay, that makes sense. Flink needs to own the state. Now, let's tackle a big challenge in distributed stream processing. Out-of-order events. Data almost never arrives in the perfect sequence it was generated, right? Especially across big distributed systems. You get network delays, different processing speeds, maybe source delays. So if you're trying to calculate, say, a 5-minute window of user activity, and some events from that window arrive after the window technically closed based on time, your results get skewed.
And this is exactly where watermarks come in. They're Flink's, well, a quite elegant solution to this. A watermark is basically a special timestamp that flows through the system alongside your data. It carries a really important guarantee. All events with timestamps before this watermark have now arrived. Think of it like a formal announcement. You might get a watermark saying all events generated before 5:00 p.m. have arrived, even if that watermark message itself only reaches Flink at, say, 5.01.15 p.m. This gives Flink a kind of configurable grace period. It ensures it has time to process data created at maybe 4.59 p.m. but delayed in transit. By processing these watermarks, Flink can make informed, consistent decisions about when to actually trigger window computations and how to handle those late events across the whole distributed system. It's a reliable signal within Flink's processing that lets operators trust its guarantee.
And you configure these watermarks right at the source of the stream, setting how long Flink should wait for those potentially late events. So like you could tell Flink to wait for events up to 10 seconds out of order based on their event timestamp.
That's exactly it. It gives that grace period before closing a time window. While Flink supports various strategies, you'll mostly see two. Bounded out-of-orderness, which is what you described, allowing lateness up to a duration. And no watermarks if strict event time order isn't critical, or events are somehow guaranteed to arrive in order, which is rare in distributed systems, and the guarantee that the watermark itself isn't out of order. That's reliable within Flink's context. Think of it like mail reception. At 5 p.m., reception signs off, all mail marked for delivery by 5 p.m. is here. The internal delivery team can then trust that signal.
Okay, the guarantee is internal to Flink's processing model. Got it. That makes perfect sense. Now that we have the foundation streams, stateful operators, watermarks, well, let's see a full example. How does a Flink job actually look? Our source material lays out a pretty clear flow. Imagine processing user clicks again. First, you define a data stream that reads from, say, a Kafka topic. That's your input source. Then come the transformations. You might apply a key-by operation on user EAD. This logically groups events, like creating a separate mini-stream for each user. On these keyed streams, you could define a tumbling event time window maybe 5 minutes long. These are discrete, non-overlapping windows based on the event timestamps. Within each window, you'd apply an aggregate operation. Maybe just count the clicks per user in that 5-minute window. And finally, you define the sink. Where do the results go? Maybe you send these aggregated counts to an Elasticsearch cluster for dashboards or searching. So that shows a whole pipeline. Ingest from Kafka, transform with keyed windows and aggregation, and output to Elasticsearch.
Exactly. And you can build much more complex things. Take the transaction processing example from the source. You can enrich transactions by joining the stream with another stream containing account details. Then, maybe calculate velocity metrics using sliding windows, looking for, say, multiple large transactions in a short time. That smells like fraud detection. Flink's CEP library complex event processing lets you define specific patterns, like find a small transaction followed by a large one within 2 minutes. Then you can union all these different alert streams, maybe deduplicate them, and send the final alerts off to an investigation system or a database. It really shows Flink's power for sophisticated real-time work.
That's a great illustration. Very powerful. Now, let's peek under the hood a bit more. How does Flink actually deliver on those promises exactly? Once processing, high throughput, low latency, even with failures.
It must be in the architecture.
Right. At the top level, Flink runs as a distributed system. 2 main types of processes. First, the job manager. This is the cluster coordinator, basically. It handles scheduling tasks, orchestrating that vital checkpointing process we talked about, managing failure recovery. It's the central supervisor.
And working for the job manager, you have the task managers. These are the worker nodes. They're the ones actually executing the bits of your job. The operators, the transformations. Inside each task manager, you have task slots. These are important. They provide memory isolation between different tasks running on the same machine. They also control how many parallel instances of a task can run there. And they allow efficient resource sharing. So each task manager offers this granular set of atomic resources that the job manager can assign work to.
Okay, so distributed work is handled. But durability, especially for stateful stuff. When things inevitably fail, how does that state survive?
Yes, back to state management and checkpointing. This is really where Flink guarantees that durability. So the job manager kicks off a checkpoint. It does this by injecting special messages, called checkpoint barriers, into the data streams. These barriers flow downstream with the data. When an operator receives a barrier from all of its inputs, it knows it's time to snapshot its current state. It pauses briefly, takes that snapshot, and writes it to a configured durable storage backend. Could be HDFS, S3, whatever you set up. Once all operators in the job have done this and acknowledge back to the job manager, the checkpoint is marked as complete.
And recovery uses these completed checkpoints.
Precisely. If there's a failure, a task manager dies, maybe even the job manager has an issue. The system can stop everything, find the latest complete checkpoint, restore the entire state of the application from that checkpoint, including operator states and reading positions in the sources, and then resume processing. This ensures no data loss and maintains those exactly once guarantees for stateful operations. It picks up right where the last successful snapshot left off. It's quite sophisticated. And just to clear up that common confusion about S3 or GCS, these are typically used for the durable checkpoint storage, not the active state Flink is working with moment to moment. The active state is usually in memory, or maybe spilled to a local disk using something like RocksDB for speed. The checkpoints are these immutable blogs, snapshots in time, that need reliable, accessible storage, which is exactly what S3 and GCS are great at.
Right. That's a critical distinction. Active state versus durable backup snapshots.
Okay, shifting gears, slightly more practical application now. In an interview, when should you actually suggest Flink? Well, it seems like a natural fit if the problem involves real-time processing of continuous data streams, right? Like the canonical example seems to be consuming from Kafka and writing processed results somewhere else, the databases, warehouses, etc.
That's generally true. But there are caveats. Flink might be overkill for very simple tasks. If you just need a basic filter or a simple field transformation on a Kafka message, a lightweight microservice consuming directly from Kafka might be simpler and less complex operationally. Flink brings power, but also overhead. So you'd propose it when you really need its strengths. Stateful processing over time, complex event processing, or precise event time semantics with watermarking, especially if the interviewer is asking about handling failures or ensuring exactly once processing. And even if you don't end up proposing Flink itself, there are lessons from Flink, as the source puts it, like its approach to resource isolation with task slots. If you have to design a custom streaming system, Flink's design choices, how it manages resources, state, fault tolerance, can be a really valuable North Star for your own architecture. Shows deeper thinking.
Absolutely. Flink is a powerful tool, definitely worth having in your toolbox for stateful stream processing. And understanding its design decisions can inspire how you build other systems, even if you don't use Flink directly.
Okay, let's move on to another really common problem in system design, one that interviewers definitely like to probe: managing long-running processes asynchronously. We're talking about operations that take more than just a few seconds, generating a big PDF report that needs to query millions of rows, maybe, or uploading a huge video file that needs transcoding into different formats, or sending a bulk email campaign if you try to do that synchronously while the user waits. It's a terrible experience. Reminds me of trying to upload a big file on bad Wi-Fi. You just stare at a frozen progress bar forever.
Exactly.
Okay.
And what do you do then? You probably hit refresh 5 times, right? Which just makes the server load worse. The problem with synchronous processing for long tasks isn't just about timeouts or server resources, though those are issues. It's fundamentally about awful user feedback. User clicks, generate report, and nothing happens. Is it working? Did it break? After a minute, they assume it broke, retry, and now you have duplicate work queued up. Even if you had infinite server scalability, the synchronous approach provides a poor user experience for anything longer than a quick response.
So what's the way out of this nightmare? It's decoupling, right? Using asynchronous worker pools. The core idea of this managing long-running tasks pattern is to split the operation. So when the user clicks Generate Report, your web server immediately does 2 things. 1, it stores the request details somewhere, probably a database. 2, it puts a small message onto a queue. And then, crucially, it returns a super fast response to the user. Something like, got it, we're generating your report, we'll notify you when it's ready. This takes milliseconds.
And that sets up what we call the async worker pool architecture. Your web servers become lightweight request routers. Their job is just acknowledging the work and handing it off quickly. The actual heavy lifting, that's delegated to a completely separate pool of worker processes. These workers are just constantly pulling jobs off that shared queue. They process the jobs at their own pace and then update the job status when done. Async means the original user request finishes immediately. Worker pool is that fleet of background job executors.
And that queue is absolutely central. It acts as a buffer, absorbing spikes. It provides durable storage, so jobs aren't lost if a worker crashes. Plus, it gives visibility. You can see pending jobs, wait times, failures, popular choices. Redis, maybe with BoolingQ for better semantics. AWS SQS is a classic managed option. RabbitMQ gives more control.
And the benefits are huge. First, independent scaling. Your web servers might need lots of small instances, while your video workers need fewer powerful GPU instances. They scale based on their load, not each other's. Second, fault isolation. If one worker crashes processing a video, it doesn't take down your API. The job just gets retried by another worker, much more resilient. And third, probably the biggest win, dramatically improved user experience. Immediate confirmation, no waiting, notification later. Users can close the tab and get on with their lives.
What about implementing the workers themselves? What are the options?
Two main paths. Serverless functions like AWS Lambda or Google Cloud Functions. Great for spiky workloads where you pay per execution. They scale automatically. Downsides are execution limits, maybe 15 minutes max, and occasional cold start latency. The other path is container-based workers running on Kubernetes or ECS. More flexibility here, good for longer jobs, potentially better resource utilization if you manage the scaling well.
Let's walk through the whole flow then, just to nail it down.
Okay, step one. Web server gets the request. It validates it, creates a job record in a database, sets that to pending. Step two, pushes just the job ID onto the queue. Very small message. Step three, immediately returns that job ID or success message to the client. And asynchronous part. Step four, meanwhile, a worker pulls the message, job ID, from the queue. Step five, worker uses the ID to fetch full job details from the database. Step six, worker updates job status to processing. Does the actual work, generate PDF, transcode video. Step 7, stores the result. For example, puts PDF in S3. Step 8, updates job status to completed or failed. Done. And the beauty is, each piece web server, queue, worker, database can fail independently, and the system is designed to recover. That's resilience.
This pattern seems incredibly versatile. When should you know to bring it up in an interview? What are the triggers? Clear signals would be any operation taking more than a few seconds, a need for specialized hardware, like GPUs for ML tasks handled by workers, or direct questions about scale or failure handling. If the interviewer asks, what if a server crashes during that report generation? Or how do you handle a sudden 10x spike in uploads? Proactively suggesting async workers is a really strong move.
And you see this everywhere. YouTube video uploads, trigger transcoding, thumbnails, captions, all async jobs. Instagram uses it for resizing photos, applying filters, and that massive fan out when a celebrity posts. Stripe handles payments, fraud checks, webhooks asynchronously. The common threads. Heavy computation, calls to slow external APIs, large-scale fan-out. If the problem involves any of these, async workers should pop into your head immediately.
But it's not a silver bullet, right? When shouldn't you use it?
Definitely overkill for simple, fast, CR-root operations. Or tasks confined to a single service that completes quickly. The source mentions simple print jobs often don't need it. Just sending data to a printer is usually fast. Don't add the complexity of queues and workers if you don't need the benefits.
Makes sense. Okay, let's anticipate some deep dive questions an interviewer might ask once you propose this pattern. First up, what happens if a worker crashes mid-job?
Right. So the job itself isn't lost because it's still technically checked out from the queue. Another worker will eventually retry it. But how does the queue know the first worker died and release the job? That's typically done with a heartbeat mechanism or a visibility timeout in SQS terms. The worker essentially has a lease on the job. If it doesn't renew the lease, send a heartbeat, within a certain time, the queue assumes it crashed and makes the job visible again for another worker. Choosing that heartbeat interval or visibility timeout is a key design choice. Too long. Jobs stay invisible for ages after a crash. Too short. You risk unnecessary retries due to brief network glitches or GC pauses, or you generate lots of heartbeat traffic. 10-30 seconds is often a reasonable starting point, balancing responsiveness and overhead.
Okay, next deep dive. What if a job fails repeatedly, like there's a bug or bad data that crashes every worker that tries it?
The poison message problem. If you just keep retrying, That bad job could consume all your worker resources and potentially block healthy jobs. The solution is the dead letter queue, or DLQ. After a job fails a configured number of times, say 3 or 5 attempts, the queue system automatically moves it to this separate DLQ. This isolates the problematic job, letting other work proceed. The DLQ then needs monitoring. A growing DLQ is a strong signal that you have bugs or bad data that require human investigation. Most queue systems have built-in support for this.
Another classic. A user clicks Generate Report 3 times impatiently. Now you have 3 identical jobs. How do you avoid doing the work 3 times?
The key concept here is idempotency. You need to design your worker logic so that processing the same logical request multiple times produces the same end result as processing it just once. How you achieve that depends on the specific job, but it often involves checking if the work has already been done before starting.
Let's talk queue back pressure. It's Black Friday. Your queue is exploding with millions of jobs. Workers are drowning. What do?
Right, unbounded queue growth is bad news. Leads to huge delays, potential memory issues. The solution is back pressure. You need mechanisms to slow down job acceptance when workers are overwhelmed. One way is setting queue depth limits. If the queue exceeds, say, 10,000 pending jobs, your API starts rejecting new requests with a system busy error. More dynamically, you should implement auto-scaling for your workers based on queue depth, not CPU. By the time worker CPU is maxed out, the queue is already backed up. Set alarms. When queue depth X, add workers. When queue depth Y, remove workers.
Okay, what about handling mixed workloads? Some reports take 5 seconds, others take 5 hours, all in the same queue. Problems.
Big problems. It causes head-align blocking. Those quick 5-second jobs get stuck waiting behind a 5-hour monster. It makes user experience unpredictable and worker utilization uneven. The solution is simple. Separate queues by job type or expected duration. Have a fast reports queue and a slow reports queue. Each can have its own pool of workers, scaled independently. This prevents blocking and allows tailored resource allocation.
Last one. How do you orchestrate job dependencies? Step 1, fetch data. Step 2, generate PDF. Step 3, email it. How do you chain these?
Yeah, this can get messy fast if you're not careful. Spaghetti code, tricky error handling. For simple chains, one worker can just queue the next job when it finishes, passing along necessary context. For more complex workflows with branches or parallel steps, you'd probably look towards dedicated workflow orchestration systems or patterns, which is maybe a topic for another deep dive itself.
Okay, the async worker pattern is super important. Identify the need, long tasks, resource mismatches, scale, and the solution becomes clear. Queue it, return fast, process in the background. All right, here's where things get, well, really interesting from a data structures perspective. We're diving into structures that let us answer questions about huge data sets with incredible space efficiency if we're willing to tolerate a little bit of error.
Exactly. These are probabilistic data structures. They're crucial when you need to ask things like, is this item in this massive set? Or how many times have I seen this item? Or how many unique items are there? But you're severely constrained by memory or storage space. And the key trade-off is accepting a small, controllable probability of error, like false positives, or getting an approximation instead of an exact answer, in exchange for potentially massive space savings compared to exact methods.
Let's start with Bloom filters. What's the core idea here? It can tell you if an element is likely already in a set you've built, or if it's definitely not in the set. That likely part is key. There's a chance of false positives.
The villager stamps analogy from the source is great for intuition. Imagine villagers each have unique stamp patterns. They all stamp a single shared piece of paper when they attend a meeting. To check if Albert attended, you look at his stamp pattern. If all the grooves corresponding to his stamp are covered in ink on the shared paper, he might have attended. Maybe other people's stamps covered those spots. But if even one of Albert's stamp grooves is clean, you know for sure he definitely did not attend. This lets you check attendance without needing a separate paper for everyone. The insight is definitive no, but only a probabilistic maybe yes. We trade certainty for huge space savings. It's a brilliant trade-off for certain problems.
And technically, how does that work?
Yeah.
No actual stamps, right?
Right. Instead of stamps, a Bloom filter uses multiple different hash functions. When you add an element, say Albert, each hash function computes an index into a bit array, and you set the bit at each of those indices to 1. To check if Albert might be in the set later, you run him through the same hash functions. You look at the bits of the resulting indices. If all of them are 1, he might be there. False positive possible. If any of them are 0, he's definitely not there. As you add more elements, more bits get set to 1. Eventually, the filter can become saturated. Almost all bits are 1, and it becomes less useful, producing more false positives. Like the analogy is paper getting completely covered in ink.
So sizing is important. Choosing the array size and number of hash functions.
Crucial. You tune those based on the expected number of items and your acceptable false positive rate, OG 1%. And it's a common misconception that Bloom filters are tiny. They save a lot of space compared to, say, a hash set, but they're not free. The example given is storing 1 billion 4-byte elements with a 1% false positive rate. That still takes about 1 gigabyte for the Bloom filter, better than maybe 4 or 5 GB for a hash set, but still significant memory. 80% savings is huge, but it's not zero cost.
Okay, so use cases and pitfalls. When do you use them?
Use cases fit 3 criteria. 1, querying for set membership. Is this in the set? 2, you're space constrained. 3, you can tolerate a false positive rate, but never false negatives. Most common example, caching. Checking a Bloom filter first to see if an item is definitely not in the cache can save you a slow trip to the database.
And pitfalls.
The big one. Standard Bloom filters do not support removing elements. Once a bit is set, it stays set. Think about the stamp analogy. You can't unstamp the paper, so they're bad for sets that change frequently with deletions. Also, issues can arise with cache eviction policies or multiple clients potentially missing cache hits if not carefully managed.
Okay, so Bloom filters for membership. What about counting?
For estimating frequencies, we have the CountMin sketch. Think of it as an extension of the Bloom filter idea, but for estimating how many times you've seen an item, it specifically provides an upper bound estimate.
Let's use the analogy again. Marbles and holes. How does that work?
Imagine each villager is assigned a few specific numbered holes, not just one. When they attend the meeting, they drop 1 marble into each of their assigned holes. To estimate how many meetings Albert attended, you look at all the holes assigned to him. Let's say he uses holes 2 and 4. Hole 2 has 3 marbles, hole 4 has 2 marbles. You take the minimum count across his assigned holes. So, you estimate Albert attended no more than 2 meetings. Why? The minimum, because other villagers also drop marbles into those same holes, inflating the counts. The minimum gives you the tightest possible upper bound based on the available information. The insight is using shared counters and taking the minimum to get a space-efficient upper bound, good enough for many applications without needing a counter per item.
And technically, it's like a grid of counters.
Yeah, basically a 2D array or matrix of counters. You also have multiple hash functions. When an item arrives, each hash function picks a row in the matrix and a counter within that row to increment. To query for an item's estimated count, you use the same hash functions to find the relevant counters in each row and return the minimum value among them. Use cases: estimating top K items, like popular videos, finding heavy hitters in network traffic. Could be used in LFU, least frequently used, cache eviction policies to estimate item popularity. The main pitfall: it's an estimate, specifically an upper bound. Don't use it if downstream systems absolutely require precise counts. It overcounts due to hash collisions.
Got it. Bloom filter for maybe in set, CountMin sketch for at most this many times. What about counting unique items?
That's where Hyperloglog, HLO, comes in. Its specific purpose is estimating the number of distinct items in a very large data set, the cardinality. For instance, how many unique users visited this web page today? CountMin sketch would just count total visits.
And the intuition. The source uses a coin flip analogy.
Yeah, it's quite clever. Imagine you keep flipping a coin. If you happen to get a really long run of tails, say 10 tails in a row, before your first heads, you'd intuitively think you must have flipped the coin a lot of times for such a rare event to occur. HLL applies a similar probabilistic idea to the hash values of the items you're adding. It looks at the binary representation of these hash values. Specifically, it looks for patterns like the longest run of leading zeros. The more unique items you add, the higher the probability that one of their hash values will, just by chance, have a very long run of leading zeros. HLL observes the longest run seen across all items and uses some statistical magic to estimate the total unique count from that observation. It's surprisingly accurate with very little memory.
So where would you use Hyperloglog?
Very common in product analytics for unique user counts, unique visitors, daily active users, etc. Used in security for things like bot detection, maybe tracking the number of distinct URLs visited by an IP address. A scraper might visit vastly more unique URLs than a normal user. Also useful in database and cache analysis, estimating the number of unique keys in a cache to understand its efficiency or sizing needs.
Okay, wrapping up probabilistic data structures. Bloom filters, CountMin sketch, Hyperloglog. They offer massive scalability gains for membership, frequency estimation, and cardinality estimation, respectively, if you can tolerate some error or approximation.
Exactly. And knowing when to suggest them in an interview and articulating the trade-offs clearly shows real depth. They solve specific large-scale problems where exact methods fail due to resource limits.
Okay, let's pivot now. We need data, and we need it fast. Let's talk about how databases actually retrieve data quickly. We're diving into database indexing, the art and science of making your queries perform well.
Right. Fundamentally, databases store data on disk, often in, well, just unordered files called heap files. Without an index, finding a specific piece of data means scanning that entire file, page by page. Incredibly slow for anything large. Indexes change the game entirely. They create structured pathways into the data. Think of a book's index or table of contents. Instead of reading every page, you use the index to jump directly to the relevant section, minimizing those slow disk reads.
And the most common type of index we encounter is the B-tree index, right? The
Yeah.
workhorse.
Absolutely. B-trees are incredibly common. They're efficient for both searches, point lookups and range queries, and updates, inserts, deletes because they maintain a balanced tree structure. Key features of a B-tree. They're self-balancing. Nodes can have many children, hundreds, even thousands, which keeps the tree shallow. Nodes are typically sized to match disk page sizes, like 4KB or 8KB for efficient I/O. Keys within each node are kept sorted. PostgreSQL uses them everywhere. Primary keys, unique constraints, most standard indexes. DynamoDB's sort key is a B-tree variant. MongoDB uses B+ trees, which are very similar. They're ubiquitous.
Okay, B-trees are common, but let's shift to a different storage paradigm, especially relevant for certain workloads. LSM trees, log-structured merge trees. These are designed for write-heavy systems.
Exactly. LSM trees optimize for write performance. When you write data to an LSM-based system, it typically goes through a few steps. First, it's written to an in-memory structure, often called a mem table, maybe a balanced tree or skip list. This is super fast because it's in RAM. Second, simultaneously or just before, the write is appended to a write-ahead log, WL, on disk. This log is sequential, so writing to it is also very fast. The wall ensures durability. If the server crashes before the mem table is persisted, the wall can be replayed. Third, once a mem table fills up, it's frozen, sorted, and flushed to disk as an immutable file called an SS table, sorted string table. These S tables are never modified. New updates or deletes create new entries in later S tables.
Okay, super fast writes. But that sounds like reads could be slow. You might have to check the current mem table, maybe older immutable mem tables, and then potentially dozens or hundreds of S tables on disk.
That's the core challenge for reads and LSM trees. And the crucial optimization that makes them practical is using Bloom filters. Each SS table typically has an associated Bloom filter. Before reading an SS table, the system checks its Bloom filter. If the filter says the key is definitely not in this SS table, the system can skip reading that file entirely. Since Bloom filters are very fast, this avoids most of the disk I/O for point lookups.
So it's a definite trade-off. LSMs for write-heavy workloads, B-trees generally better for read-heavy ones.
That's the general rule of thumb. LSM trees excel where writes dominate. Think metrics, collection, logging systems, maybe IoT sensor data. Cassandra, which is famous for handling massive write volumes, uses an LSM architecture. For typical user-facing applications with lots of reads, B-trees usually provide better overall performance. Interestingly, some databases like RoxyDB, which is often used inside other databases, are LSM-based, and systems like DynamoDB cleverly use both, picking the right engine for the job.
Beyond the big two, B-trees and LSM trees, there are other specialized index types, like hash indexes. You mentioned they're fast for exact matches.
Very fast for key if-value lookups. But they're less common in disk-based databases because B-trees are almost as fast for exact matches and support range queries, key value, and sorting, making them more versatile. Hash indexes really shine in in-memory databases like Redis, where the main access pattern is direct key lookup.
What about spatial data? Finding things nearby on a map. Restaurants within 5 miles. The standard B-tree on latitude and longitude struggles here.
Yeah, a composite B-tree index on lat, Wagulon, doesn't really understand 2D proximity well. It would query one dimension than the other. R trees are designed for this. They work by indexing multidimensional data using bounding boxes. An R tree might group nearby restaurants into a bounding rectangle, then group those rectangles into larger ones. Queries traverse the tree, efficiently pruning branches whose rectangles don't overlap the query area. They adapt to the data's clustering, unlike rigid grid structures like quad trees. Though for very high write spatial scenarios like tracking thousands of moving Uber drivers, R-tree updates can be costly due to rebalancing. In-memory solutions like geohashing, often using Redis, might be preferred there.
And for searching inside text, like finding blog posts containing the word database, B-trees only help with prefixes.
Right. For full text search, you need inverted indexes. These are the backbone of systems like Elasticsearch and Lucene. The process involves breaking text into tokens, words, normalizing them, lowercase, stemming, removing stop words like a, the. The index then maps each unique term back to a list of documents and positions within them where it appears. This makes searching for words incredibly fast. Modern systems add relevance scoring, TF-IDF, BM25, fuzzy matching, phrase queries. It's a whole field. The trade-offs are significant storage space for the index and complexity in updating it.
Okay, let's quickly cover some advanced strategies for boosting read performance even further. First, covering indexes.
A covering index is a clever optimization. It includes all the columns needed by a specific query directly within the index itself. So if your query is select title, create a dot from posts where useRead equals 123, a normal index on useRead helps find the rows, but the database still has to go fetch title and create dot from the main table data, the heap file or clustered index. But if you create an index on posts, useRead include title created, the database can satisfy the entire query just by reading the index pages. It never needs to touch the main table data. This is called an index-only scan and can be much faster. The trade-off is a larger index.
And partial indexes, indexing only a subset of rows.
Yes, very useful. If most of your queries only care about, say, active users, you can create an index like on users email where status is active. This index only includes rows where status is active. It will be much smaller and faster to scan than a full index on email. It also reduces write overhead, as changes to non-active users don't need to update this index. Highly effective when queries target a specific subset.
Excellent. Indexing is clearly fundamental. Now, let's broaden the scope to the fundamental challenge of scaling read operations overall. It's almost physics, right? Reads usually vastly outnumber writes 10.1, 100.1, even more is common. A single database server will eventually hit a wall.
Absolutely. A single popular item, like a viral video or news article, can generate enormous read traffic. The approach to scaling reads generally follows a logical progression. First, optimize within the database indexing, query tuning. Second, scale the database horizontally by adding more servers. Third, layer in external caching for the hottest data.
Okay, step one. Optimize within the database. We just talked about indexing as the first line of defense.
Crucial. Turn ON, full table scans, into O-log-N index lookups is often the biggest single win you can get. B-trees are the standard tool here.
Then there's denormalization, intentionally duplicating data to avoid expensive joins.
Yes. Relational databases love normalization for data integrity, but joins across multiple large tables can kill read performance at scale. Pre-calculating things, like an order summary that includes user and product details, and storing it directly with the order record, avoids those costly joins on read.
And materialized views take this even further, pre-computing results of complex queries.
Exactly. If you have an expensive aggregation, like calculating average product ratings across millions of reviews, doing that on every page load is infeasible. A materialized view runs that query periodically in the background and stores the result. Reads then just query the simple pre-computed result table. Fantastic for dashboards and analytics.
Okay, so you've optimized queries, denormalized, maybe used materialized views, but your single database server is still melting under, say, 100,000 reads per second. What's next?
Next step is scale your database horizontally. Add more database servers to show the load. The most common pattern here is using read replicas. This uses leader-follower replication. You have one primary leader database that handles all writes. Then you have one or more secondary follower databases that replicate data from the primary and handle only read queries. This distributes the read load and also provides high availability. If the primary fails, a replica can be promoted. Replication can be synchronous, safer, slower writes, or asynchronous, faster writes, potential for stale reads.
And that potential staleness is the big catch with async replication lag.
Precisely. If a user writes to the primary and immediately reads from a replica that hasn't received that write yet, they won't see their own update. This is the classic read your writes consistency problem. Managing and monitoring lag is critical.
What about sharding? We mentioned it for write scaling, but it helps reads too, right?
It does, indirectly. By splitting your data across multiple shards, each shard handles reads for a smaller data set, reducing the load on any single machine.
Sure.
You might shard functionally, users versus products, or geographically, users in Europe versus users in Asia. But sharding adds significant complexity, especially around cross-shard queries or transactions. For purely read scaling, replicas and caching are often preferred first.
Which brings us to step 3. Add external caching layers, often the biggest bang for the buck for read performance.
Absolutely. Caching frequently accessed data in a fast in-memory store like Redis or Memcache can dramatically reduce load on your databases and provide sub-millisecond response times. Common patterns include cache aside, check cache on misfetch from DB and populate cache, write through, write to cache, then DB, and write back, write to cache async, write to DB. Cache aside is probably the most common.
But caching introduces its own big problem, keeping the cache consistent with the database. Invalidation strategies are key here.
Yes, this is where caching gets tricky. Simplest is time to live. TTL data just expires after, say, 5 minutes. But that means potentially stale data for 5 minutes. More explicit invalidation involves deleting or updating cache entries when the underlying data changes in the database. This can be done synchronously, hurts write performance, or asynchronously, right behind invalidation, introduces a small staleness window. Other strategies include tagged invalidation, grouping related keys, version keys, changing the key on update, probabilistic early refresh, serve stale data while refreshing in background, and even caching deleted items to filter out reads for recently deleted things. Choosing the right strategy depends heavily on consistency requirements.
And what about that killer problem? The hotkey. Millions of requests hitting the exact same item in the cache.
Yeah, even an in-memory cache server can get overwhelmed by a truly hot key. Solutions include request coalescing. If multiple requests for the same missing key arrive at once, only send one request to the database and serve the result to all waiters. Or cache key fanout, also called sharded cache keys, intentionally store the same hot data under multiple slightly different keys, e.g., item 1, item 2, item n. Clients randomly pick one of the keys, distributing the load across multiple cache entries, potentially on different servers. And for global scale, don't forget CDNs. Caching static assets and even dynamic API responses at edge locations close to users drastically reduces latency. Range requests are also crucial for efficiently downloading large files from CDNs or blob storage.
Okay, putting it all together for an interview. When do you bring up read scaling? Be proactive. If you're designing an API endpoint that looks like it will get heavy read traffic, feed sample, view product details, read user profile, explicitly call it out. Say, this endpoint could get hammered, we should consider read scaling. Then walk through the progression. First, we'll optimize the queries and ensure proper indexing. If that's not enough, we'll add a caching layer like Redis using cache aside. If the database itself is still a bottleneck, we can introduce read replicas.
And when not to overdo it. Don't introduce replicas and complex caching for write-heavy systems where reads aren't the bottleneck.
Yeah.
Don't add complexity for small-scale apps. And be very careful with systems requiring strong consistency caching and async replication. Make that much harder. Tailor the caching strategy to the data-specific consistency needs.
A common deep dive. Your queries get slower as the dataset grows. Why and what do you do?
This almost always points to missing indexes, leading to full table scans. As the table grows, the scan takes proportionally longer. The fix. Add appropriate indexes on the columns used in where, join, and order by clauses. Turns that ON scan into an OLOGN lookup. Simple, but fundamental.
That covers read scaling beautifully. Now let's flip it. Scaling write operations. This is often where systems hit really hard limits, where a single database just can't keep up with the ingestion rate. Interviewers love digging into write bottlenecks.
They do. But first, a crucial point. Don't underestimate modern hardware. A single beefy server today has immense power, massive RAM, fast SSDs, high-speed networking. Know your numbers to know. Understand roughly what a single well-provisioned machine can handle before immediately jumping to complex distributed solutions. Avoid premature optimization.
Good point. Start with the hardware, then consider database choices specifically geared towards writes.
Right. Some databases are architected for write throughput. Cassandra is a classic example, using that LSM tree structure we discussed. Its append-only commit log allows very fast sequential writes to disk. It can often handle 10x or more writes per second than a traditional relational database on similar hardware. The trade-off, typically, is potentially slower or more complex reads. Other examples include time series databases like InfluxDB or TimescaleDB, optimized for high-volume, time-ordered data, or column stores like ClickHouse for analytical writes.
And general optimizations you can apply to any database for writes.
You can often tune the write-ahead logging, WAL mechanism, maybe batching commits more aggressively. You can disable expensive features you don't need, like complex triggers, or maybe even foreign key constraints during peak load, if absolutely necessary. Be careful. And critically, reduce index overhead. Every index you have needs to be updated on writes. Fewer indexes mean faster writes, but potentially slower reads. It's always a trade-off.
Okay, so you've maxed out a single node. The next step for writes is usually horizontal sharding, right? Splitting the data across multiple servers.
Correct.
Sharding distributes the write load. Each server or shard only handles writes for a subset of the data. Redis Cluster does this by hashing keys to slot numbers distributed across nodes. Consistent hashing is another common technique to map keys to servers. The absolute key to successful sharding is selecting a good partitioning key. You want a key that distributes writes as evenly as possible across all shards. Hashing a high cardinality identifier like user or post-id is usually best. Avoid keys with skewed distributions like country code, where one shard might get massively overloaded.
And distinct from horizontal sharding, splitting rows, there's vertical partitioning, splitting columns.
Yes, this is about splitting a single table into multiple tables based on access patterns. Imagine that social media posts a table again. It gets writes for content, writes for likes, views, metrics, and maybe writes for analytics. You could vertically partition it into post content, write once, read many, post metrics, very high write frequency, and post analytics, append only. Each part can now be stored, indexed, and scaled independently, isolating the high-frequency metric writes from the content reads.
What about handling sudden write bursts? Like a viral tweet causing a massive spike in likes, overwhelming your normally scaled system. Auto-scaling database instances takes time.
Right. Bursts need buffering or shedding. The most common buffering approach is using write queues. Kafka, SQS, RabbitMQ. Your API quickly writes the request, example user 1223 liked tweet 456, to the queue and returns success. Background workers then read from the queue and apply the writes to the database at a sustainable pace. This smooths out the burst. Crucially, this is for short-lived bursts. If your database is always overloaded, a queue just hides the problem and increases latency. You also need to consider the user experience. The like might not appear instantly.
And if buffering isn't enough or the data isn't absolutely critical,
then you look at load shedding. When severely overloaded, you might have to start rejecting some writes based on business priority. Maybe you drop less critical analytics events to ensure core transactions succeed. Or like the Uber example, drop an older location update if a newer one is coming soon anyway. It's about graceful degradation to prevent total system collapse.
we can also make writes themselves more efficient through batching and hierarchical aggregation.
Absolutely. Individual writes have overhead, network latency, transaction setup. Batching combines multiple logical writes into a single database operation. This can happen in the client application, in an intermediate processing layer, or even configured within the database itself. For example, buffer writes for 100 meters before flushing. Batching amortizes the overhead. Hierarchical aggregation takes this further, especially for counters like likes or views. Imagine processors handling likes for subsets of posts. They aggregate counts locally for, say, 10 seconds, then forward the aggregated batch to a higher-level processor that merges results. This drastically reduces the write load on the final storage layer, at the cost of some aggregation latency.
Even with good sharding, you can still get hotkeys and write systems. That viral tweet's like counter, all hitting a single shard. How do you handle that?
This is tough. If one specific key gets an overwhelming number of writes, sharding by post-ed doesn't help. Two main approaches. One, split all keys, fixed K. You preemptively write data for every post across, say, 10 different keys. Post 1 likes 0, post 1 likes 1, post 1 likes 9. Writes pick a random suffix. Reads have to query all 10 and sum the results. This spreads the load but multiplies storage and read cost by K2. Split hotkeys dynamically. Only split the counter for a key when it becomes hot. Maybe post 123 likes becomes post 123 likes 0 to post 123 likes 99 when its write rate exceeds the threshold. Reads and writes need a mechanism, maybe a central lookup, to know which keys are currently split. These techniques work well for aggregatable data like counters, but not for atomic data like updating a user profile.
Okay, bringing it back to interviews. When do write scaling patterns come up? Proactively identify write bottlenecks using back-of-the-envelope math. If you estimate millions of users generating content or events per second, flag that as needing sharding or queuing. Suggest sharding by user ID, using queues for rate limiting or smoothing bursts.
Common scenarios: social media feeds, sharding posts, partitioning metrics, maybe hierarchical aggregation for likes, real-time analytics ingestion, write-optimized DBs, queues, batching, search indexing, batching updates, live comments on streams, hierarchical aggregation.
And the caution: don't over-engineer. Each write scaling technique adds complexity and potential trade-offs like eventual consistency or increased latency. Solve the problem you have, don't invent new ones with premature scaling. Okay, we've scaled reads, scaled writes. Now for arguably the trickiest part: ensuring data consistency when multiple things happen at once. Dealing with contention. Contention is when multiple processes or users try to access or modify the same resource simultaneously. Think booking the last seat on a plane or two people editing the same document. Without careful handling, you get race conditions, inconsistent data, all sorts of chaos.
Exactly. The core issue is that read, modify, write operations usually aren't atomic in a distributed world. There's that tiny window between reading a value and writing the updated value where someone else can sneak in and change it. At scale, those tiny windows cause big problems.
We often start by thinking about transactions. They give us atomicity within a single database, right? All or nothing operations, like booking that concert ticket, reserve the seat A and D, create the ticket record, or neither.
Right. Atomicity is crucial, but as we discussed, atomicity alone doesn't solve concurrency issues. If Alice and Bob both start atomic transactions, both read available seats, one, both calculate new seat 0, and both atomically update the seats to 0, you've still sold 2 tickets for 1 seat. They didn't coordinate between their transactions.
So we need more. One approach is pessimistic locking, assuming conflicts will happen and locking resources up front.
With pessimistic locking, you explicitly acquire a lock before you proceed. In SQL, this is often done with select devil. For update, when Alice's transaction runs this, it gets an exclusive lock on the relevant rows. If Bob's transaction tries to read or lock the same row, it just waits until Alice commits or rolls back, releasing the lock. This serializes access to the contended resource, preventing the race condition. It gives precise control, but can hurt concurrency if locks are held for long or if contention is high, as threads end up just waiting.
Databases also provide built-in mechanisms via isolation levels.
Yes, databases try to manage this for you. PostgreSQL, for example, has levels like read committed. Default can have non-repeatable reads. Repeatable read sees a consistent snapshot from transaction start. And serializable. Serializable is the strongest. It guarantees that transactions behave as if they ran one after another sequentially.
Yep.
It prevents all concurrency anomalies. The downside, it's expensive, and if the database detects a conflict that would violate serializability, it forces one transaction to roll back, requiring your application to have retry logic. So it's a trade-off. Serializable handles everything, but can be slow and require retries. Explicit row locks, select for update, give you more fine-grained control over specific contention points.
The opposite approach to pessimistic locking is optimistic concurrency control, OCC. Assume conflicts are rare, proceed anyway, but detect them after the fact.
Yes, exactly. With OCC, you read a value along with some version identifier, could be a version number column, a timestamp, or even the value itself if appropriate. You do your work, and then when you go to write the update, you make it conditional. Update where art8n version equals expected version. If another transaction updated the row in the meantime, the version will have changed, and your update statement will affect 0 rows. That signals a conflict, and your application logic needs to catch that, maybe reread the data, and retry the whole operation.
Okay, that handles contention within one database. What if the data spans multiple systems? Alice's bank account is in chart A, Bob's is in chart B. A single DB transaction can't cover both. We need distributed coordination.
The classic heavyweight solution here is two-phase commit, 2PC. You have a central coordinator managing the transaction across multiple participants, the databases or services involved.
Phase 1 is prepare. The coordinator asks all participants, can you commit this transaction? Participants try to do the work locally, lock resources, and respond yes, prepared, or no. They log their intent. Phase 2 is commit or abort. If all participants said yes, the coordinator logs commit and tells everyone to commit permanently. If any participant said no or timed out, the coordinator logs abort and tells everyone to roll back.
Crucially, the coordinator must write its final decision, commit or abort, to a persistent log before notifying participants. This is vital for recovery if the coordinator crashes. 2PC guarantees atomicity across systems, but is complex, slow, locks held during prepare, and fragile coordinator failure or network partitions are painful.
For simpler needs, maybe not full distributed transactions, but just ensuring only one process does something system-wide, we have distributed locks.
Right. If you just need mutual exclusion across different services or nodes, common implementations. Redis with TTL. Use Redis's atomic set key value and px milliseconds command, and x means set only if p doesn't exist, px sets an expiration time, TTL. Fast, simple, Redis handles expiry cleanup. Downside. Redis is a single point of failure, unless using Redis Cluster Sentinel, need to handle Redis unavailability. Database columns. Use a table in your existing database with columns like locky, ownerid, expiresat. Use atomic database operations to acquire the lock. Leverages database ACD properties. Slower than Redis, needs background job to clean up expired locks.
So when do these contention patterns come up in interviews? What are the signals? Look for scenarios with limited resources and concurrent access. Booking tickets, auction bids, flash sales with limited inventory. preventing double booking, double charging, ensuring consistency for critical data like account balances or inventory counts under high load, any mention of potential race conditions in distributed operations.
Common interview scenarios where these apply. Online auctions, OCC often fits well for bids. Ride-sharing dispatch, maybe application-level status flags or distributed locks leases for drivers. Flash sale inventory, OCC on counts, maybe short-lived pessimistic locks or queuing for the very last item. Review systems like Yelp OCC using review count as the version is often better than using average rating.
And the advice remains, don't jump to complex solutions too quickly. Try database-level locking, select for update, or OCC first if the contention is within a single database. Avoid adding distributed coordinators or lock managers unless absolutely necessary.
Start simple and predictable, usually with pessimistic locking within the DB, and escalate complexity only if the requirements demand it.
Let's quickly hit some deep dives on contention. Coordinator crashes during 2PC.
The nightmare scenario. Participants are stuck holding locks, waiting for a decision. Solution requires coordinator failover, another node takes over, and transaction recovery. The new coordinator must be able to read the crashed coordinator's persistent transaction log to determine the outcome of in-flight transactions and tell participants to commit or abort accordingly. Without that durable log, 2PC is unrecoverable.
Choosing the right version for OCC. What if the value doesn't always change?
Right, like the average rating example. If two concurrent reviews don't change the average but do change the count, using average rating as the version for OCC would allow both updates, losing one review's contribution to the count. Solution. Use a column that always changes on update, like review count, or add an explicit monotonically increasing version column. DynamoDB's conditional rights handle this internally.
Performance on a really hot resource, everyone hammering the last concert ticket.
When contention is extremely high on a single item, locking, pessimistic or optimistic retries, can lead to terrible performance or thundering herds. The ultimate solution for serialization is often queue-based processing. Put all requests for that specific resource, e.g. Ticket Concert XTDD, into a dedicated queue processed by a single worker thread. This forces sequential processing for that resource, eliminating contention entirely. Trade-off is latency, but it keeps the system stable. That's incredibly insightful. Contention is definitely a deep topic. Okay, last major pattern for today. Handling large binary objects, blobs. We're talking user uploads like videos, high-res images, big data sets. If you're dealing with files, say, larger than 100 MB moving through your API, this pattern is pretty much mandatory.
Absolutely. The fundamental mistake is trying to proxy these huge files through your application servers. It's incredibly inefficient, burns CPU, RAM, and network bandwidth on your servers, just shuffling bytes around. Your servers become a bottleneck. The solution is all about orchestrating access and letting the client interact directly with blob storage for the actual data transfer.
And that solution is direct uploads with presigned URLs. Explain that flow. The client, web browser, mobile app, first asks your application server, hey, I want to upload a large file. Your server doesn't accept the file. Instead, it communicates with your blob storage provider, like AWS S3, Google Cloud Storage, Azure Blob Storage, and generates a special time-limited URL. This URL, called a presigned URL, SAS token, or signed URL, depending on the cloud, grants temporary permission to upload a specific object directly to a specific location in blob storage.
Your server sends this unique URL back to the client. The client then uses this URL to upload the file directly to S3 GS Azure, completely bypassing your application servers for the heavy lifting of data transfer. This is efficient for everyone. The client likely uploads faster because they connect to a storage endpoint geographically close to them. Your servers are freed up to handle other API requests, and these presigned URLs have built-in security. They expire, valid for only 10 minutes. They can specify expected file size limits, content types, etc. A URL for a 500MB image upload won't work for a 500MB video.
Okay, direct upload bypasses servers. What about making it robust for really large files, like gigabytes? Connections drop.
For that, you need resumable uploads, typically implemented using the storage provider's multi-part upload capabilities. The client breaks the large file into smaller chunks, for example, 10 MB each. It uploads these chunks independently, often in parallel. One chunk fails due to a network error. The client only needs to retry uploading that specific chunk, not the whole file. The storage service tracks the uploaded parts using a session or upload ID. Once all parts are uploaded, a final API call completes the multi-part upload, assembling the file.
Important note, incomplete multi-part uploads still consume storage space, so you need lifecycle policies on your storage bucket to automatically clean up abandoned uploads after a day or two to avoid unnecessary costs.
Good point on cleanup.
Now, once the file is successfully uploaded directly to blob storage, how does your backend know it's there and ready for processing? Like transcoding. This is usually handled via event-driven processing. Most blob storage services can emit events, example S3 event notifications, when a new object is created or finalized, like after a multi-part upload completes. These events can be published to a message queue, SQS PubSub, or trigger a serverless function, Lambda. Your backend workers subscribe to this queue, or are triggered by the function, receiving notification that file X is ready in bucket Y. They can then start processing it, transcoding, analysis, etc., without ever having proxied the upload itself.
Okay, upload handled. What about fast downloads? Downloading a large file directly from S3 in Virginia when your user is in Sydney can be slow due to latency.
That's where CDNs, content delivery networks, come in for downloads. You configure your blob storage as the origin for a CDN distribution. The CDN caches copies of your popular files at edge locations all around the world. When the user in Sydney requests the file, they hit a nearby CDN edge server, which likely has a cached copy, providing a much faster download.
And for large file downloads, even from a CDN, resumability is important too.
Yes, using HTTP range requests, this allows the client, browser, download manager, to request specific byte ranges of the file. For example, range bytes 011485759. If the download gets interrupted, the client knows how much it received and can resume by requesting the next byte range. CDNs and blob storage almost universally support range requests for efficient large file delivery.
So when to use this direct upload-download pattern in interviews seems pretty clear-cut. Yeah, the rule of thumb is, if the requirements involve users uploading or downloading files larger than maybe 5,100 millibeats, immediately suggest this pattern. Bypassing your servers using Presigned URLs is the standard scalable solution.
Common scenarios: video platforms, YouTube, Vimeo, image sharing, Instagram, Flickr, though images might be smaller, file sync storage, Dropbox, Google Drive, software distribution, basically anywhere users move large binary blobs around.
And when not to use it.
For small files, 10 millia, maybe even 50 eleba, uploading small profile pictures, configuration files, or JSON payloads directly through your API server is usually fine and avoids the added complexity of generating signed URLs. The overhead isn't worth it for small data. Also, crucially, think about abuse prevention. You usually don't want uploaded content to be immediately publicly accessible via the direct storage URL. The upload should trigger a back-end workflow that processes, validates, and potentially moves the file to a different location or sets appropriate permissions before making it available. Don't just give users direct write access to your public content bucket.
Wow. Okay, we have covered an incredible amount of ground in this deep dive on system design. Seriously, from Flink stream processing internals to async task management, probabilistic data structures, deep into database indexing, scaling reads, scaling writes, wrestling with consistency and contention, and finally handling large blobs. It really is a vast landscape.
It really is, and I hope the key takeaway isn't just memorizing these patterns or technologies. It's about understanding the fundamental trade-offs, the why behind each decision. Why choose LSM over B-tree here? Why use OCC instead of pessimistic locking there? When is a queue appropriate? When is it overkill? Being able to articulate those reasons based on the specific requirements and constraints of the problem, that's what demonstrates strong system design thinking.
Absolutely. It's about building that mental toolkit and knowing when and how to apply each tool. We really hope this deep dive, this sort of contribution to your system design magnum opuses, helps you not just in interviews, but in becoming a more thoughtful, more effective engineer day to day. We encourage you, revisit these concepts. Look at the systems you use every day. How might they be built using these patterns? How would you design them differently now?
Because at the end of the day, in this world of ever-increasing scale and complexity, building resilient, efficient, user-centric systems really comes down to mastering these fundamental principles.
Perfect.
So the final thought to leave you with is, what aspect of system design, maybe one we touched on today or something new, will you deep dive into next to continue building your understanding?